This is a little walk through Hankel functions. So let's start off by considering cylindrical waves. So in cylindrical coordinates. But I'm going to consider a very, very, very simple, and of course a simple cylindrical wave that only depends on the radial coordinate. So I'm kind of imagining that normally, of course, we would have r for our particular point. We would have its, phi, its r, and its z, like that. But I'm saying it's the same for all z. But I'm also saying it's the same for all theta. So it purely is like a radial situation. And for example, if I had a slit that was infinitely long in all directions, like that, and I imagined perfectly cylindrical waves coming off of this, like that. And this is then on this side, at any rate, this is the sort of situation I'm thinking about, where the electric field would only depend on the radius going around. It doesn't depend on z. It doesn't depend on theta. Now, in that situation, we can take our Laplacian like this, and we can get rid of anything that depends on phi, whose gradient depends on phi, and so we're left with this much nicer and simpler differential, which is this Helmholtz equation, purely radial. And this is one that you can solve, but for large r, if you do this, if we solve it for large r, you will end up with something that looks like this. Like this. And this is a sort of, well, it's a cylindrical wave. It's the eigenfunction of this. Okay, so, and if I want to put my time back in, like this, I simply put it back in, switch back on the time component, because that was separated a while ago, and I'll get something like this. And at that moment, my cylindrical waves will move off. If this is a top view, then after, when r is quite large, I will be having cylindrical waves radiating off to infinity. So this is a cylindrical wave where there's no variation in z, no variation in phi. So it's an idealized and symmetrical situation, but that may well be an approximation to many real-world events. And it certainly is a good first starting location. Okay, now let's now put back our phi and the z dependence. So I want to now go back to considering this in more detail, and I'm going to say that my wave number can be split up into a radial component and a z component. So my z will be the e to the I kz, the rate at which it propagates along the z axis, and my k is just 2 pi over lambda. So when you, and often I'm going to refer to kr squared as gamma squared, and kz squared is often referred to as beta squared. So for example, in optic fibers, that's the propagation constant. Now, just to recap, what we do is we separate the functions. We end up with the z variation being e to the I k z, and we end up with the phi variation being e to the I m phi, where m is an integer. And the reason why it takes that form is due to periodic boundary conditions. And then we end up with Bessel's equation, which is this. After a bit of manipulation, like that. Okay, And just to be absolutely clear, so my wave function would be the solution of this, which by the way will depend upon whatever my m is, because it's involved here, e to the I m phi, e to the I k z. So what we have, just to remind you, is, and could I just say this, when I say you, I really mean me, because I don't think anybody's actually watching these, but they are entirely for my own memory aids, so therefore I don't apologise if I get anything wrong. So this is a function of r and theta, and we can sort of imagine whatever this function of r and theta is, we can imagine it propagating in the z direction, and that's my propagation going on here. Now, just to recap, if kr squared is greater than 0, i.e. kr is real, so it's real variable, then we get the oscillating functions, which is my Bessel function of first kind and the Bessel function of the second kind. And the Bessel function of the first kind looks like this. If it's J0, that's the only one that doesn't start from 0. And J1 and everything else starts from 0. Now, I just correct myself. Previously, I had been drawing this in like this, as if it had 0 gradient. It doesn't have 0 gradient. It actually has a gradient of a half. At least J1 does. But what does happen is my peak gets further out, and it goes, so the peak takes longer to get to the peak. But just to be clear, I think I've been drawing it, or I've got into my head that J1 sort of starts off with a nice 0 gradient. It doesn't. It actually starts off with a gradient of a half, so it does this. Little correction. And Y, well, they look like this, and their main feature is that they have this asymptote, they diverge at minus infinity. So these are the two solutions we get when we have a real value of kr. Now, if on the other hand we have kr squared is less than 0, so kr is complex, it's got imaginary, then we often write it as kappa squared is minus kr squared. So that simply means, returning back to my Bessel equation, that essentially all I'm doing is questioning the sign of this. I'm simply saying, well, if this is positive, i.e. kr is real, then it's going to be J1 and JL and YL. Actually, I should really, I don't know why I did, I seem to be using L interchangeably, but since I called this M, I should call it JM or YM. It seems that some people use M and some people use L, it doesn't matter. Now, if this is negative, then we have our Bessel functions of the second kind, which are IM or IL and KL. So let's look at each one. So if I have IL of kappa R this time, then these look like this. This is I0, and they're all and it's the only one that doesn't start from 0. And all of the other ones start from 0 but have slightly less acceleration, like this, I1, I2. And in the case of the modified Bessel functions of the second kind, which are KL, kappa, R, and remember kappa is just minus kr squared, then we have them like this. So they're decaying functions, exponential looking decaying functions, and this is k0, k1, etc. So basically, when this function is greater than nothing, I have periodic, and when this function is less than nothing, I have exponential growth or decay. And that's what decides whether I have my Bessel functions of the first kind or my Bessel functions of the second kind. Now, that means we have to consider, we know when we're dealing with a Helmholtz equation situation, then we'll have, presumably what we will often do is divide the problem into sort of zones. Like, for example, imagine, say, a load of concentric regions of different refractive index, like this, A4, and this goes off to infinity, right? So if we were trying to solve Helmholtz equation in this situation, then the first thing I would say here is in this first region, we can't have an asymptote at 0. And let's imagine, so in this situation, we can't possibly have anything. We can only have Jm, and potentially we could have Im as well here, because that's not asymptotic in that region. In the next region, well, now we could have them all, because we don't have to worry about infinity, or we don't have, so the solutions here would be combinations of Jm, Ym, IL, or at least we would need to consider these, all of them, because none of them are diverging, and they're all perfectly good solutions. Actually, we would consider them, but we would probably rule them out depending upon whether kr squared is greater than 0 or less than 0. Now the next thing's true here. Again, I could have potentially all of them in the next region. But then finally in this region, we now have the situation where this is tending to infinity. Now some of these Bessel functions will explode as they go to infinity. So we definitely can't have IL, but I could potentially have KL, and I could potentially have YL as well, going off to infinity. In this case, this would be kind of oscillating off to infinity. So since it's oscillating, it would be taking energy rather than behaving evanescently. Okay, so we would need to make a decision about which Bessel functions and modified Bessel functions to include in this situation, and then we would sort of enforce boundary conditions to decide which ones it is. And usually the usual boundary conditions we would enforce would be things like continuity and continuity in the first derivative. Or we may well need to go right back to the Fresnel boundary conditions in the electric field E and H to decide. Okay, now let's consider what happens when R tends to infinity, because we're kind of talking about modelling these symmetrical waves, cylindrical waves. So JL will tend to the root of 2 over pi r, cosine r minus L pi over 2, pi over 4. I've noticed I've gone back to using L rather than M, but no worries. YL, on the other hand, this another oscillating solution, but this behaves like sine when we get far away, everything else remaining the same. Obviously when we get much further away, the R is going to dominate these terms. It's just going to go as cos R and sine R. And for my modified Bessel functions, it does genuinely go as the exponentials, so root 2 pi r, and KL is root pi over 2r e to the minus r. So this is the asymptotic behavior. Right, now finally, now we're going to introduce the Hankel function of the first kind. The first Hankel function of the first kind is written as HL1. So it's parameterized by L, which is the same L in the Bessel functions, and it's equal to the Bessel function of the first kind plus I times the Bessel function of the second kind with the same parameter L. So all I've done is I've added a complex amount, and this might seem to be a bit pointless, but remember that this would have to, remember that solutions of my Helmholtz equation are always of the form a Bessel function of the first kind. The oscillatory ones, solutions, are always of this form. So it should be a perfectly acceptable solution to the Helmholtz equation, given that A and B are constants. There's no reason why they can't be complex. But the real reason for choosing it is look what happens when it becomes exponential. So as R tends to infinity, and I see I just slipped into using R, my Hankel function of the first kind will tend to 2 over pi r cos r. In fact, I'm going to put this as kr in, plus I root 2 over pi r sine krr. In other words, my Hankel function will tend to 2 over pi r e, and I'm going to get I k r, which is nothing more than my cylindrical wave. My cylindrical wave, which is radiating away. So, in other words, my Hankel function of the first kind very nicely shows outward radiating waves. So my outward cylindrical waves that we mentioned right at the beginning, where we looked at a very simplified version of my Helmholtz equations, look like this. And this is, a Hankel wave is exactly like this. So my Hankel function of the first kind is an outgoing wave then. So let's look at my Hankel function of the second kind now. So the Hankel function of the second kind, let's put KRR in, is just the difference. It's the conjugate, complex conjugate. Like that. And in the same way, analogously, as R tends to infinity, now I get this. And this is a wave converging, a converging cylindrical wave, converging on a cylindrical focus. So this is quite interesting, because whereas previously my previous so so for example, I could start off with a cylindrical source, and then I would know that it's radiating away, and I know that we can model these with Hankel functions of the first kind, like that, going away from the radius. But the Hankel function of the first kind allows me to have all of the detail much closer as well, if I actually put the actual Bessel functions back in. The only place where I can't know what it is actually on the source, because that's going to be a singular situation. Now imagine I have some sort of optics, some sort of cylindrical lens like this, and I create a converging situation now, going to a cylindrical focus. Well, now I've got my Hankel functions of my second kind in order to study what goes on in here. So in other words, I've essentially, by this method has essentially solved my Helmholtz equation in these regions, whereas previously I was just using this sort of long distance approximation. If I look close to my source, then I'm going to have a singularity here, but I can get quite close because there's a nice approximation for my at least for my Hankel function with L as 0, and it's approximately 1 plus 2i over pi natural log of x over 2. So there is a limiting situation, so you can get arbitrarily close to that source and see what happens. And what's interesting is it goes as a natural logarithm, which of course tends to minus infinity. Right, so last of all, just like there's a link between cos x and cos x, so cos x is cos of ix. In the same way, there's a nice link between Bessel functions of the second kind and Bessel functions of the first kind, simply by putting in complex argument. So the nicest one is the Bessel function of the first kind and the modified Bessel function of the second kind, and just by putting this argument ix in, you do get the other one within a complex constant. But there's also one for the Bessel functions of the second modified Bessel function of the second kind, a bit more complicated though, and this is this. So this requires my Hankel function of the first kind. So if I put a complex ix into my Hankel function of the first kind, I end up with my Bessel function of the second kind, so this isn't quite so nice. Anyway, the only use of that is to show that there is this sort of relationship between them that's very similar.